For the subglotal part, probably we cannot do that much because it's just the pressure which is produced by the muscles. But the glottal, we can extract pitch, which is the vibration rate of the vocal folds in the larynx. Is the same for the infant. So we can see that for the phonation, it is usually less than 700. For hyperphonation, is more than 700. And for dysphonation, it's noisy vibration. So I just put an example here for you to see. If you look at this example, this is a spectrogram of a normal cry sample. These areas, like here, they are phonation part. And the fundamental frequency is around 300, 400 hertz. It has beautiful harmonics that you can see here. So they are almost the same as voiced part that we have in the speech adult. Whereas here, that's actually I put a circle around that, we have hyperphonation. It's very hard for the machine to extract that kind of pitch, that kind of high pitch frequency. It's around 1000 or even more than 1000 hertz. And these are the most crucial parts recognized and abnormalities. Because as you can see later on is that the hyperphonation part of the cry speech are the most discriminative parts. So we still have a lot of problem with extracting pitch for higher than 1000 hertz. Usually all of the pitch estimation works very well less than 700 hertz because they are designed for the human adult, not for the babies or for the infants. So this is one example of the pitch, and you can see that it's very difficult to extract the fundamental frequency over 600, 700 hertz. So actually I put a result of the machine pitch estimation here, but it's very faint. So as you can see, it's totally missed this area, and it's considered it as some sort of dysphonation, which means it doesn't have any fundamental frequency. So this is one challenge that we have. We have to work on very, very accurate pitch estimation which are optimized for the infant cry. Now, the next part would be supraglottal. So we used to extract formants as the resonant frequency of the vocal tract and one of the best indicators for the filter modeling of the vocal tract. So let's see what formants tells us in the infant cry. Are they quite useful or informative? Actually, formants are very, very critical. It has different reasons. One of the reasons is that the formants for two modes of the crying infants, dysphonation and phonation, are usually is different from 1000 to 4500. If you remember, for hyperphonation, what was this frequency? Do you remember for hyperphonation? Exactly. So then the pitch for hyperphonation would be confused with the first formant of dysphonation or phonation. So for us, it's very important to have a very robust formant extraction technique that can avoid that problem. So the next thing would be, okay, we cannot really compare the phonation of one infant with hyperphonation of another infant because it's totally misleading. If we compare these two, then you would see that if the phonation has, for example, pitch frequency of 300 and the hyperphonation of 1000 hertz, then you would say, okay, this is abnormal because the pitch frequency is very high. But it's not really true because this is hyperphonation, this is phonation, pitch contribution. This is one good example to show how difficult is that to distinguish between these two when the fundamental frequencies is a bit higher than 400, for example. They are really the first formant and the fundamental frequency are getting very close in this region. And as you can see, this is a very, very kind of, high pitch signal here as well. So we have done a very, very preliminary result, because now we have a very small database and we are developing that database. I just want to show you that how pitch and formants can be distinguishing different normal and pathological cries. So this is a normal cry. This is the PDF of the normal cry for pitch. This is for asphyxiated, and this is for the kids who are suffering from hearing impairments. You can see that the pitch is very good in discriminating between normal and abnormal, but not very good in distinguishing between these two pathologies, right? But what we figure out is that the formant tree is actually the best feature that can discriminate these three. So normal, asphyxiated, and deaf with formant tree can be somehow separable. So this is a very preliminary result. We haven't actually investigated the other features, but
so this formant is the first formant.
No, it's the third formant. The third formant is the most
third formant.
Exactly.
And that's exactly what you can.
Yes.
So for first formant and
No. The first formant, second formant, they are not very useful. Because again, there's so much confusion with the fundamental frequency. So the third formant is the best one that can detect the abnormalities. It's what we found us so far. Yes, you can combine the features. You can actually find out which of them is good for each pathologies. So this is the next steps that we are, getting into that, because for that you need lots of data, and then you need to collect it from the pediatricians, because they are the people who can really tell you if this is this disease or not, because we are not, in that stage. But if we want to see what could be done, is that first we need to see how acoustic manifestation of the certain pathologies such as asphyxia and hearing impairment in cry signal exist, and how we can correlate that one to the anatomical abnormalities. And the other thing which still we have issues even in speech adult is that how to isolate subglottal filter and source contributions from the speech signal. So in the cry is even much harder, because you have three different parts: supraglottal, glottal, and vocal tract model. How you can have a system or a kind of analysis on the cry signal that can find the contribution of each of them separately. And then you should be able to probably again synthesize or reconstruct the cry signal again from these three different models. So this is again one aim. And also definitely we need to look for the alternative acoustic features to fundamental frequency and formants, since their extraction is quite hard and sometimes it's very confusing in hyperphonation part. So what kind of derivative of pitch frequency we can use? For example, is pitch contour or kind of other modeling useful in that case? Can we find a unique model for the pitch contour of the infants? Again, these are the other questions. Or for formant extraction, is there any other alternative that we can use? For example, a spectral centroid or frequency modulation features. We have to look into that. But the challenges mainly is that in the cry, we have a pre-classification stage. As I said, we never can compare the hyperphonation with the phonation of another cry type, because they have different characteristics. So if we make any mistake in the first class and we classify them in the wrong category, then it will affect the final result. So this is very important for us, the pre-classification. It's something like phoneme classification, but it's just 3 phonemes. you can say. And also